In the first part of section 4.2, we've already talked about how to graph polynomial functions if they are already factored. Okay, so what we looked at in the first half of this section, maybe we would look at the factors and find the roots, understand the multiplicity of these roots, and then look at the degree and the sign of the leading coefficient to determine the end behavior. Alright, now what we're going to look at today is how we might factor a polynomial and then do all those things that we did last time. This is not significantly different than what we did with cubic functions in section 4.1. Alright, so as you will remember, with cubic functions, if we were going to do polynomial division, which most students do not prefer this strategy, what we would do if we had a cubic, well, we want to put this in the form, we're going to say qx plus p. Okay, well, the factors of this constant here had to be a factor of my constant term of my cubic, and then this q here had to be a factor of this leading coefficient. Let's see if that makes sense. If we had some polynomial here that was factored, okay, and then we expanded this out. Well, if I have x's and x's here, okay, this constant term is going to be the product of whatever these numbers are here. Okay, so going backwards, if we know this, well, p must be a factor of a naught, or our constant term. Similarly, if we had some numbers here in front of these x's, and we wanted to factor, go from our expanded form to our factored form, well, we would look at this coefficient, the leading coefficient here, to figure out what these are. So here, q is going to be a factor of my leading coefficient, which we're calling a sub n, and p would be a factor of our constant term, which we're calling a naught. Okay, that is similar to what we did with cubics, only instead of saying a sub n and a naught, I think we might have called them a and d. We named those coefficients. Alright, now most students do not prefer polynomial division. As you saw, even with a cubic, it could become quite cumbersome. So we had this bookkeeping scheme, which we called synthetic division. Now, remember, if I have a factor of qx plus p, okay, well, the root is when that factor equals 0. Okay, so if I were to solve this from x, we might get qx equals p, and then, oh, that would be negative p, wouldn't it? Then we get x is negative p over q. Alright, so since we're not concerned about this negative right here, because either of these factors could be positive or negative, so for synthetic division, the potential roots are going to be p over q, okay, where p is a factor of a naught and q is a factor of a sub n. So this is our constant term, and then this is a factor of our leading coefficient. Okay, and again, I didn't worry about that negative because the factors here could either be positive or negative divided by the factors which are either positive or negative. All right, now for what we're doing here, I'm going to stick with synthetic division. If you prefer polynomial division as we did with the cubics, you're welcome to give that a try. All right, so here's what we want to do. We want to first factor the polynomial. Okay, this is the new stuff, as we did with cubics. But then parts B, C, D, E, and F, all of those are what we did in the first half of this section. All right, so let's start with our factoring here. To get my potential roots, I'm going to look at all the factors of 15 over all the factors of 1. Well, that's nice because the factors of 1 are 1 and negative 1. So I just need the positive and negative factors of 15. So my potential factors might be 15, negative 15, 1 and negative 1, 5 and negative 5, 3 and negative 3. Alright, now here I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, I have 8 potential factors. Now, if you remember what we talked about last time, if this is degree 4, at most we could have 4 roots, possibly less. So we know that all of these are not going to work. Okay, now we can use our strategy of trial and error, pick one, use synthetic division, and see if we get a remainder of 0, like we did with the cubics, or we'll talk about in a minute how you might use your calculator to make sure you pick a root that works well. So let's say I started with, I'm going to try, let's start with 1 here. Alright, so my root I'm going to put right here, 1. Alright, now inside I have a coefficient of 1 for the quartic term, negative 2 for the cubic, negative 16, 2, and 15. Alright, and we are hoping that we end up with a remainder of 0 down here. So I'm going to bring down my 1. 1 times 1 is 1. Negative 2 plus 1 gives negative 1. Alright, this is the same as we did with the cubics. 1 times negative 1 is negative 1. I add and I get negative 17. Okay, 1 times negative 17 is negative 17. I add and I get negative 15. Okay, 1 times negative 15 gives me negative 15. I add and I get 0. Alright, so we know that this, because I got a factor of a remainder of 0, that this 1 is a root. Now, 1 could be a root again, it could be a double root, or we could have some of these. So what we have so far, if my root is 1, my factor is going to be x minus 1. Okay, and these are the coefficients of what's now going to be a cubic. So this is going to be x to the third minus x squared minus 17 x minus 15. Now this is the only thing that's different from what we did with cubics. When with our cubics, once we pulled out a factor, we had something that was quadratic here, and then we could factor it using our algebra. The only difference here is now I'm going to have to do synthetic again to get a second factor out of there before I get it down to something that's quadratic that we can factor using algebra. Alright, now we want to factor this piece one more time before we get it down to something that's quadratic. Now, my factors of negative 15 over 1 are the same as we have listed here. So it could be any of these. It could be, and it could also be 1 a second time. It could be a double root. Let's try, I'm just gonna at random pick 1, 3. Let's see if 3 would work. Alright, so I'm gonna put 3 outside. And then inside, we're going to put these coefficients. 1, negative 1, negative 17, negative 15. Alright, so I'm going to bring down the 1. 1 times 3 is 3. I add these and I get 2. Alright, 3 times 2 is 6. I add these and I get negative 11. Okay, 3 times negative 11 gives me negative 33. And when I add that, that is definitely not 0. That is negative 48. Okay, so I know that 3 is not a root. Alright, now at this point you see it could be a lot of incorrect guessing before I find a second root. So what I'm going to do to make sure I pick correctly is I'm going to let the calculator help me here. So I'm going to go to my graph menu. Alright, and I'm going to enter my equation. Alright, now I need to pick a window. Now these roots could be anywhere from negative 15 to 15. So I might choose a viewing window initially of negative 16 to 16 and do a zoom auto. Alright, now I cannot see what's going on here. My roots would be somewhere around here, but I can't see exactly what's going on because polynomial functions get so large so quickly. Alright, but I think I can eliminate a root of negative 15 and 15 from this graph. Okay, so now I'm gonna try a second window. Let's say, what would my next roots be? Maybe negative 5 and 5. So maybe I'm going to go negative 6 to 6. Alright, I'm getting close. I think there might be a root at 5. I can't exactly tell what's going on here though, so I'm going to pull my window in a little closer. So let's say the next root might be over here at negative 3 possibly. Alright, so let's go maybe negative 3.5 to 5.5. Alright, now I can see what's going on here. It looks like there is a root at 1, 5, negative 1, and negative 3. Okay, now to verify that, we can use our gsolve menu to find the roots. Shift, graph solve, root. Alright, and there is 1 at negative 3. I use my right arrow to jump to the next one. 1 at negative 1, 1 at 1, and 1 at 5. Alright, so it looks like we have 4 roots here. So I can now use the calculator to help me pick the potential root that I know is going to work out here. So we've done 1, let's try now -1. Alright, so I'm going to try -1. So my coefficients here, see this one didn't work, right? So I'm just going to get rid of that one. Alright, my coefficients are 1, -1, -17, -15. Alright, so I'm going to bring down my 1. -1 times 1 gives me -1, add and I get -2. -1 times -2 is +2, I add and I get -15. -1 times -15 is +15, and we get a remainder of 0, which is what we were hoping for from the calculator. Alright, so let's see if we can factor this now. So I know that we've pulled one factor out here, so f of x. I've pulled one factor out of x minus 1 for my root of +1. I've pulled a factor out of x plus 1 for my root of -1. And then I'm left with x squared minus 2x minus 15. Alright, now this piece, this quadratic, we can factor using our algebra. So I'm going to copy these factors. Alright, so we have an x and an x. Now I need 2 factors of 15 that have, or 2 factors of -15 that have a sum of -2. So I think that would be 5 and 3. Alright, and which one do I want to make negative? I want -2, so I need a -5 here and a +3. Let's see if that would work. -5 times 3 gives us the -15. Then inside we'd have -5. X, outside we'd have +3x, which would give us a -2x. Alright, so that was the new part. Now, giving the roots their multiplicity, the y-intercept, describing the end behavior using function notation, and graphing the polynomial, all of this we did in the first half. So let's see, we have completed part A right here. Alright, now for part B and C, we can go from the factors to the roots, and we have roots of x equals 1, -1. Now if the factor is x minus 5, the root would be +5, -3. And each of these factors shows up once, so they are all single roots. Which means they're going to cut through the x-axis. Alright, now for the y-intercept, part D, I'm just going to plug in 0. Alright, so if I plug in 0 here, well, this goes to 0, this goes to 0, this goes to 0, this goes to 0, so I am left with +15. Alright, for part E, we need to describe the end behavior using function notation. Alright, so we're going to have the limit as x approaches infinity of f of x, and the limit as x approaches -infinity of f of x. So to answer this question, we are going to look at two things. I'm going to look at the degree, which is 4, which is an even degree. Alright, and then I'm going to look at the leading coefficient, which is positive leading coefficient. Alright, so if my degree is even, both ends are going to go in the same direction, and if that leading coefficient is positive, they are both going up. Okay, so this is going to, one end is going up, then we're going to have, some stuff going on right here, and then the other end is going to go up. So from that, we know that the limit to the right, we're going up, and the limit to the left, we're also going up. Alright, and then lastly, we need to graph this. Alright, now I didn't leave myself much room to do this, but I think we can make do here. So f, we want to graph this. Alright, here. So I'm going to have a y-intercept at positive 15. Alright, I'm going to have a root at negative 3, negative 1, both of those are single roots, positive 1, and positive 5. Okay, and my both ends are going up here. So I'm going to start off here. I'm going to go through through negative 3, then back up through negative 1. I'm going to pass through 15 on my y-intercept, down through positive 1, and up through 5. And hopefully, although I did not draw this beautifully, this looks very, very similar to what we had here with the calculator. Now, if you wanted to see that y-intercept, we could go Shift, Graph Solve, y-intercept at 15. But I don't think anyone needs a calculator to evaluate this function at 0. Alright, so let's look at another example. Here we have a quartic function, something degree 4. So I'm going to have to use synthetic division twice to pull out two factors before I can get this down to something that's quadratic, and then use a little algebra to factor that quadratic. So my potential roots are going to be the factors of negative 8 over the factors of negative 1. So that would be 8, negative 8, 4, negative 4, 2, negative 2, 1, and negative 1. Okay, so what we're going to do here, we're going to use our calculator to help us pick roots that we know would work. If we didn't have this technology, we could potentially, pick 4 or 5 that didn't work before we found one that works. So I'm going to enter my equation here into y1. Alright, now I need to think about a window. My smallest potential root is negative 8. My largest is 8. So to make sure I get those in the window, I'm going to go negative 9 to 9 and do a zoom auto. Alright, and this window is quite bad. Yes, we can't see what's going on here. So from this though, I can eliminate negative 8 and 8 from my potential roots, and we're going to zoom in a little more here. So our next, we might look from negative 4 and positive 4. So I'm going to set my window negative 5 to 5 to make sure we get those in there. and do another zoom auto. Okay, this is looking better. It looks like -4 might be one. I can't exactly see what's going on here, but I can definitely eliminate +4. Alright, so I'm going to zoom in a little bit more. Let's go maybe -4.5 to 2.5. Alright, now it looks like we can see what's going on here. So, to find these roots, I'm going to go Shift, Graph Solve, Root, and it looks like one is at -4, then -1, 1, and 2. Alright, so it looks like from the calculator we have -4, -1, 1, and 2. Alright, so I have used the technology to help me pick roots for my synthetic division that I am pretty sure are going to work. So let's start with 1. Alright, so I'm going to bring down my -1. 1 times -1 gives me -1. Add -2 and -1 to get -3. Multiply here to get -3. Add to get 6. Multiply to get 6. Add to get 8. Multiply to get 8. Add, and we get a remainder of 0. But we knew that was going to work for us. Alright, now let's try, let's say maybe -1. So this root of 1 gives us a factor of x minus 1. And then the remaining coefficients are -1, -3, 6, and 8. So I bring down my -1, multiply to get +1, add to get -2. Multiply to get +2, add to get 8. Multiply to get -8, add to get 0. Great. Now we've got this down to something that's quadratic, which we can factor using our algebra here. So I'm going to call this g of x. I factored out an x minus 1 for my root of x, for my root of +1. I have x plus 1 for my root of -1. Then I have -x squared minus 2x plus 8. Alright, now it's a little difficult sometimes to factor with a negative coefficient of this quadratic, so I'm going to factor that out. So if I factored out that negative, this term is going to be positive. The next term is going to be positive, and then this term is going to be negative. Alright, so I factored out that negative. I'm going to copy these two factors. Alright, so I know if x squared, I have an x and an x. Now I need two factors of -8 that would add to give me 2. So I know one's negative and one's positive. I think 4 and 2 would work well. So which one do I want to be positive? I think I want my 4 to be positive and my 2 to be negative. Let's see if that works. my last term here, negative 2 times 4 would give me negative 8, which is what I was looking for. Then inside I have negative 2x, outside I have positive 4x. Yep, those add up to positive 2x. Alright, so we have factored, so we have completed part A here. Now part B. We need to identify the roots and their multiplicity. So let's see, my roots are going to be 1, negative 1. I have a factor of x minus 2, so that would give me a root of positive 2, and x plus 4 would give me a root of minus 4. Okay, each of these factors show up once, so these are all single roots. Alright, which answers part C about their multiplicity. Alright, for part D, we need the y-intercept, which I'm going to plug in 0 here. And we're just left with that constant term right here of negative 8. Alright, now E, for part E, we need to look at our degree and the sign of our leading coefficient. Alright, so we have an even degree, which is 4. Alright, so we know both our limits are going the same direction. Now because this leading coefficient here is negative leading coefficient, we know both of those ends are going down. So our limit notation would be the limit as x approaches infinity of g of x. So as I go to the right, I am going down, so that would be negative infinity. Alright, and then the limit as x approaches negative infinity of g of x is also going down, so another negative infinity. Alright, now we can put all this back together and graph this, or look at our graphing calculator to help us graph this. Alright, so my roots are at negative 4, negative 1, 1, and 2, and then my y-intercept is down here at negative 8. Okay, both my ends are going down, so I'm going to start off here, go through negative 4, back down through negative 1, y-intercept of negative 8, up through positive 1, and then back down through 2, which hopefully resembles what we had in the calculator here. And again, if you wanted to get that y-intercept in the calculator, I gotta go shift, graph solve, y-intercept, and yes, we get a y-intercept of negative 8. Alright, in this next example, our potential roots are the factors of 4 over the factors of 1. So that would be positive 4, negative 4, positive 2, negative 2, positive 1, and negative 1. Alright, now what makes this more interesting is, do you see that I do not have a cubic term or a linear term here? So when we do our synthetic division, we're going to have to use some zeros to hold those places. But as we've been doing, let's use our calculator here to help us make sure we pick good roots for our synthetic division. So I'm going to enter my equation here into y1. And I'm going to pick a window here from -5 to 5, because that would cover all these potential roots here, and do a zoom auto. Okay, so I think from this graph that we have here, we can eliminate 4 and -4. Alright, so if I want to come into possibly 2, let's go -2.5 to +2.5. And do a zoom auto. Alright, now it looks like I can see what's going on here. If I use my gsolve root, it looks like we have a root at -2, -1, 1, and 2. Alright, so it looks like we have 4 roots, the 4 remaining here. So from a calculator, it looks like all 4 of these would work. Alright, so I might start with 1. Now, I have a coefficient here of my quartic term of 1. There is no cubic term, so I'm going to put a 0 there to hold that place. Then -5 for my quadratic. There is no linear term, so I'm going to put a 0 there, and then a 4 for my constant term. Alright, so we multiply to get 1, add to get 1, multiply to get 1, add to get -4, multiply to get -4, add to get -4, multiply to get -4, add to get a remainder of 0. So that one worked as we thought. Alright, next I might try -1. So I'm going to put these coefficients here. And continue with our synthetic division. Multiply to get -1, add to get 0, multiply to get 0, add to get -4, multiply to get 4, add to get a remainder of 0. Alright, so what do we have here? We have that h of x is, we have a factor of x minus 1 for my root of +1, a factor of x plus 1 for my root of -1, and then what's remaining? We have 1x squared plus 0x, so we don't have an x term, a linear term, minus 4. Okay, now we can factor this quadratic piece using a little bit of algebra here. Alright, x and x. So I need 2 factors of -4 that add to be 0. Well, they have to be the same. So that would be, or the same in magnitude at least, that would be -2 and +2. Great. So we have completed part A. Alright, now for B, my roots here are, what are my roots here? We had -2, -1, 1, and 2. Alright, for part C, all of these are single roots. Alright, I haven't seen a double root yet, so maybe I need to pick some better examples next time. D here, we need the y-intercept. We can do that. We're just going to plug in 0. So h of 0, well, my first term is 0, my second term is 0, I'm just left with that constant of 4. Alright, now we need to describe the end behavior here using function notation. Alright, so I have an even degree and a positive leading coefficient. Alright, so the even degree tells me that both of these limits are going in the same direction, and because it's positive, they are both going up. So we have that the limit as x approaches infinity of h of x, when I go to the right, I'm going up, so that would be positive infinity. And then the limit as I go to the left is also going up, positive infinity again. Okay, and now I think we can put all this back together and graph this. Alright, so we had roots at -2, -1, 1, and 2, a y-intercept up here at 4, and both of my ends are going up. Alright, so I'm going to go down here through -2, up through -1, pass through my y-intercept of 4, down through 1, and then up through 2. Which hopefully we can see here in our calculator. So we did pretty well there. Alright, now this example here is degree 5. So if it's degree 5, I'm going to potentially have to do synthetic division 3 times to pull out 3 roots before I get this down to something that's quadratic that I can factor using algebra. So my potential roots here are the factors of 45 over the factors of -1. Alright, so it could be 45, -45, maybe 15, -15, maybe 5 and -5, 3, -3, 1, -1, and hopefully I haven't missed any there. Alright, so there's quite a few there. So as we've done in the past, we're going to use the technology to make sure we can pick good roots here. So -x to the 5th plus 11 x to the 4th minus 38 x to the 3rd plus 39 x minus 45. So once we get that entered in there, we need to now pick a window. So my smallest potential root is -45, my largest is 45. So I might start with a viewing window from -46 to 46 and do a zoom auto. Alright, now it looks like I can eliminate -45 and 45. Alright, now let's reel this in. Next might be -15 to 15, so I might set my window -16 to 16 to make sure I can see those roots. And do a shift zoom auto. Alright, I still can't see what's going on, but I can at least eliminate 15 and -15. So now maybe 5 and -5. So I might set my viewing window -6 to 6 and do a zoom auto. Now I can eliminate -5, but I can't really tell what's going on at 5 yet. So next we might try, let's see, negative 3 to 5. So let's go negative 3.5 to 5.5. Still can't see much, but I can eliminate that negative 3.5. So maybe let's go, what's my next root? Negative 1. So maybe let's go negative 1.5 to 5.5. Alright, now we can see what's going on here. So if I go to my gsolve menu and root, it looks like negative 1, 1, 3, and it looks like 3 is going to be a double root, and 5. So it looks like we're going to have 4 roots where 3 is a double root. Alright, so let's see if we can do synthetic division to get those results. So maybe let's start with 1. Negative 1, 11, negative 38, 34, 39, and negative 45. Bring down my negative 1, multiply and get negative 1, add and get 10. Multiply and get 10, add and get negative 28. Multiply and get negative 28. I add and get 6. Multiply and get 6, add and get 45. Multiply and get 45, add and get 0. Great. Now maybe I'll try negative 1. Alright, bring down my negative 1, multiply, add, multiply, add, multiply, add, multiply, and add. Alright, now because this is to the degree 5, I'm going to need to do my synthetic division one more time. So maybe let's try 3 here. Multiply here and get 3, add and get 14. Alright, then 3 times 14 is that 52? No, 42. Okay, I'm going to add here. Alright, and bring down my negative 1. 3 times negative 1 gives me negative 3. I'm going to add here and get 8. 3 times 8 gives me 24. I'm going to add here and get negative 15. 3 times negative 15 gives me negative 45. I add and get 0. All right, now we're getting close here. So we'll call this f of x. We've got a factor of 1, so that would be x. I'm sorry, we have a root of 1, so that'd be a factor of x minus 1. A root of negative 1, so that'd be a factor of x plus 1. A root of 3, so a factor of x minus 3. And then negative x squared plus 8x minus 15. Alright, we can factor out a negative from this quadratic term. So I'm going to get negative x minus 1, x plus 1, x minus 3. Alright, and then once we factored out that negative, we get an x here and an x here. I need two factors of positive 15 that would give me negative, a sum of negative 8, so they both have to be negative. One is 5 and the other is 3. Okay, so we have factored that. We have completed part A. Now, for part B and C, my roots here are going to be, let's see, do we have positive factor here would give me a negative root. So that would be negative 1, 1, 3, and 5. Okay, so we only have 4 roots, but this 3 here is going to be a double root. Okay, and then the others are single roots. Now for part D, the y-intercept, I just need to plug in 0. So when I plug in 0, we are left with that constant term of negative 45. Part E, I need to describe the end behavior here. Okay, so we have a odd degree, so we know those ends are going in opposite directions, and because it's negative, as I go to the right, I'm going down. As I go to the left, I am going up. So the limit as x approaches infinity of f of x, as I go to the right, I'm going to go down negative infinity, and the limit as x approaches negative infinity, as I go to the left, we're going up, which is positive infinity. Alright, and now let's see if we can put all this back together and graph this. Alright, so I have a root here at negative 1, 1, 3, 5, and then a y-intercept way down here at negative 45. Okay, because I have an odd degree with a negative leading coefficient, I know that I'm going to be going down on this end, up on this end. Okay, and then I have to remember 3 is a double root, so I'm going to bounce off that one. So I'm going to go down, cut through at negative 1, pass through negative 45, cut through at 1. Now 3, I'm not going to cut through the x-axis, I'm going to bounce off because it's a double root, go back up, and then down through 5. Alright, and hopefully that's what we got in our calculator. Let's just double check here. Yes. cut through -1, cut through 1, bounce off of 3, and down through a root of 5. Alright, what we're doing here is we're going backwards. I've given you the graph, and we want to see if we can figure out one possible equation. Now, we are not going to expand these equations. We're going to leave them factored. That would take us all day. So we want to look at the roots in the y-intercept, the end behavior, and see if we can work backwards to come up with an equation here. So first, I have a double root at -2. So I'm going to have two factors. If my root is -2, the factor would be x plus 2. And I have two of them because this is a double root. Alright, then I'm going to have a factor of x plus 1 for my root, single root of -1. And then we have a root at 1.5. Okay, so that could be x minus 1.5, or you might do something like 2x minus 3 would also give us a root of 1.5, but this is, I think, is the simplest. Okay, now we're not done yet because we have to make sure this y-intercept is correct. So if I call this f of x, if I were to plug in 0 here right now, now I don't want to have to expand all this out. That would be too much work. So if I plug in 0, this term that's going to go to 0, so that'd be 2. That's going to go to 0, so that'd be 2. That'd go to 0, and that would go to 0. So I would end up with 2 times 2 times 1 times -1.5. Alright, so what does that give me? 4 or times -1.5. Would that be -6, I think? Let's see, 2 times -1.5 would give me -3. -3 times 2 would be -6. Alright, that is not what we wanted. We wanted 24 up here. So what could I multiply -6 by that would give me a y-intercept of positive 24? I think that would be a -4. So let's see if this works. F of x, if I had -4 times x plus 2, x plus 2, x plus 1, x minus 1.5. Alright, let's see if this one would work. If I did f of 0 would give me -4 times 2 times 2 times 1 times -1.5. Would that give me the y-intercept we were hoping for? -1.5 times 2 is -3 times 2 is -6 times -6 times -4 gives me 24. Yes, that's what I was looking for. Alright, so this is one possible equation. Now there are different variants of this. For example, I might have a -2 out here if I called this piece 2x minus 3. But this is one possible solution. Now, my both ends are going down, so I should have a negative leading coefficient, which I do, and it should be to an even degree. 1, 2, 3, 4 x's. Yep, that would be an even degree. Alright, so let's look at this next one here. I have a root at -1, so that factor would be x plus 1. Looks like a double root at 1/2. So I could do 2x minus 1 times 2x minus 1, or what I'm going to do is I'm just going to do x minus a half. That's probably the easiest. And then I'm going to have 2 factors of x minus 2 for this double root right here. You can see, does everyone see? This one is going to be a double, and this one is a double root. Alright, so let's plug in 0 and see what we get here. Alright, so if I plugged in 0, I would get 1 times negative a half times negative a half times negative 2 times negative 2, which would give me positive 1. Alright, and I think that's what we were looking for, a y-intercept of positive 1. So we got it our first go around. Our equation here, f of x would be x plus 1. If I wanted to condense this, I could say this is x minus a half squared. That's the same thing as saying x minus a half times x minus a half, and then x minus 2 squared.